This is a CT dataset of a 3D printed aluminum manifold. You can rotate the 3D rendering of the actual part and look at it from various directions. Besides the 3D rendering, you can also use a CT dataset to virtually slice through a part and to look at its internal structures. And so you can zoom in, and whenever you find something suspicious, like here in this case the remains of some supportive structure, you can look at those structures from any direction you like. So the combination of having the 3D geometry from the actual part captured as a virtual 3D model and the possibility to slice through the part from any direction you like makes CT a very powerful tool in the non-destructive inspection of parts. Before one can look at the CT dataset in the way I'm doing it here, of course this data first needs to be generated. And in this video, I would like to explain how the basics of CT imaging work. This is what an industrial CT looks like. Let's have a closer look. So if you look into a CT, there are three components. There's an X-ray source, there's a sample positioning stage, and there is a detector. For this video, I'd like to keep it simple. So I use this yellow cylinder for the X-ray source. This will be our sample positioning stage. And then I use a schematic black screen as a symbol for the detector. As a sample, I'm using this cube. Next, we turn the X-ray source on. This results in having an X-ray image of the cube projected onto the detector. The sample positioning stage with the sample is then rotated, which results in X-ray images of a rotating sample. The CT volumetric dataset, kind of like what I showed at the beginning of the video, is then being reconstructed based on these X-ray images of the rotating sample. The distance between the X-ray source and the detector is referred to as FDD, or focus detector distance. And then there's a second distance of importance here, which describes the distance between the X-ray source and the sample, and this is called the FOD, or focus object distance. The ratio of FDD over FOD describes the magnification with that the sample is projected onto the detector. So let's consider a case where the sample is larger. And in this case, this sample is too large to being projected onto the detector at the current magnification. To account for this, one would have to move the sample, or the sample positioning stage with the sample, closer to the detector, and then it will fit again. Then, of course, this increases the FOD and it decreases the magnification, which is the ratio of FDD over FOD. We can also look at the opposite case of a very small sample. So here the sample fits well onto the detector, and actually there's lots of space left on the detector. So in this case, the sample can be moved closer to the X-ray source, which results in an increased size of the projection of the sample onto the detector. Positioning the sample close to the X-ray source means having a small FOD and a high magnification. Next, I'd like to talk about the focal spot, which is the spot on the X-ray source where the X-rays originate from. The size of the focal spot itself will cause some uncertainty in the way on how the X-rays pass by the object, and consequently in how the object is projected onto the screen. So in a more realistic scenario, this kind of looks like this, that actually there's some blur or some unsharpness in the X-ray projection of the sample on the detector. So now let's consider the same case for the small sample that is being positioned very close to the X-ray source and consequently projected onto the detector with a very high magnification. As you can see, at high magnification, the unsharpness that is caused just by the size of the focal spot has a much more severe effect, has a much higher effect. So the image will be projected even more blurred onto the detector than it was the case at a lower magnification. There even can be the case where, despite having a high resolution due to the high magnification, that the level of detail in the data is less than in the lower resolution scan due to the unsharpness of the X-ray images. To avoid this, it will be beneficial to keep the focal spot as small as possible, especially for high resolution scans. The focal spot size itself is a consequence of the things that are happening in the X-ray source. So in the X-ray source, there's a filament that emits electrons. And opposite to the filament, there's the target. And the focal spot actually is generated on the target. Between the filament and the target, there's some high voltage. The target itself will have a positive charge, whereas the side of the filament will have a negative charge. As a consequence, the electrons will be accelerated towards the target in this electric field, and they will be focused towards the focal spot on the target. For a sample with a material that is more X-ray dense, we need to increase the source voltage to have a higher acceleration of the electrons, which will also cause our focal spot to become larger. You might have guessed it already. With the larger focal spot, as shown before, the geometry of the X-ray beam changes again, causing a higher unsharpness of the images that are being projected onto the detector. Switching back to a lower voltage is no option in this case because we need high energy X-rays to penetrate the dense sample material. So the only option in this scenario is to lower the X-ray tube power by lowering the electron current in the tube, which also will result in a smaller focal spot again. And again, having a smaller focal spot will help to have sharper images, especially at high magnifications. However, as we now lowered the X-ray tube power by lowering the electron current, we have to take into account longer exposure times on the detector to get a good X-ray signal. So you can see CT imaging can be quite complex, and there's many parameters to consider. So for the X-ray source, these parameters are the acceleration voltage, then there's the electron current, and of course it's the focal spot size of the X-ray source. So for the sample positioning stage, the parameters to consider are first, of course, the material of the sample to be inspected. Then, of course, the size and the geometry of the sample have an impact as well. And then what needs to be considered is the position of the sample and the rotation steps over the 360-degree rotation. Finally, for the detector, the parameters to consider are the position, again, so the distance between the detector and the X-ray source, then the sensitivity of the detector, and the exposure time, so the time that it takes to capture one individual X-ray image. So with this, I'm coming to the end of my video, which only covered the hardware side of CT imaging. So talking about reconstruction and software analysis will be a totally new chapter in the world of CT imaging. But as a first step, of course, it's important to understand the hardware side of the process, and this is what I meant to explain.